Hello, welcome to this talk. I am Natalie Rosenzweig, Director of Name Architecture, and I am delighted to present you with our concept Afterlife, which proposes to convert and retrofit commercial building stock into new vibrant residential hubs. Name architecture is an international practice. Based in London and Paris, our vision is immersed in the elegance of the city from which we draw inspiration. We believe in leveraging the innovation potential of collaboration through combined expertise. For each project, we form bespoke collaborations with a trusted network of experts to enrich our work. In doing so, we design architecture that is both visually interesting and technologically innovative. Many of our projects involve working with existing buildings and providing them with a new lease of life. Afterlife is a design concept that proposes to retain rather than demolish existing structures and retrofit them to achieve enhanced environmental and social facilities. According to statistics, the average lifespan of a building in Britain is 132 years. However, in the commercial sector, the average lifespan is 25 to 30 years only. So, designing the future from scratch isn't really sustainable. We must design for the future within the context of today. And, as we know today, the greenest building is the one that already exists. But this is not yet a standard in our industry. The UK construction and demolition sector currently produces 120 million tons of waste each year. This is nearly 60% of all UK waste. On average, 95% of this can be recycled, and we know that reuse of materials lowers carbon emissions and utilizes their functionality. The photo on this slide is quite emblematic. On the left, a building being demolished, while on the right, a new structure is coming up. The current economic model actually encourages demolition. This is an environmental and economic issue, but it becomes a social one too. Demolition works are disruptive and cause significant noise and pollution. Here on this slide, we see the building from the previous image, which was now demolished. So what about our existing built environment? The construction and maintenance of the built environment accounts for about 45% of UK carbon emissions, and commercial buildings are responsible for 3% of the UK's greenhouse gas emissions. For the construction and demolition sectors to become more sustainable, the design industry must change its approach to existing buildings. Existing buildings are a fixture of the built environment that can be improved and not necessarily erased. As we have long experienced in our practice, the purpose of a building can be altered, and the environmental performance of a building can be improved. Well, we ask a question. How much demolition could be avoided with a thoughtful architectural strategy? How can retrofitting become more of the norm? The notion of retrofitting is not a new one. It considers the installation of new building technologies and systems into a structure that was previously designed without these features. Maintaining elements of the building reduces material waste and lowers carbon emissions, whilst having the potential to increase the building efficiency. However, this is still carried out in rather established construction methods today. Another aspect of traditional retrofitting is to modify the existing fabric to enhance the environmental conditions, mainly by adding insulation internally. A further retrofit principle is to reuse the building for a different program. Converting listed buildings is something we deal with a lot in our practice. However, retrofitting must not be reserved for historic buildings only. It must be incorporated into the design of the ordinary. What we are proposing here is a novel way to consider retrofitting. By harnessing the interstitial space, in other words, the leftover space. Stemming from the observation that typical dimensions, for example floor-to-ceiling heights, of commercial buildings compared to those of residential buildings result in a surplus for the latter, we examined whether this surplus space could be used to enhance environmental and living conditions. Residential floor-to-floor story heights are typically lower than those of non-residential uses. Can we thus use this interstitial space surplus to improve environmental conditions within existing structures retrofitted for residential use, and thus enhance the quality of living? This was the foundation of our thoughts and the outset of our design proposal, which concentrates on the potential of existing buildings to be reused. The use of interstitial space can be exploited in many ways to enhance environmental and living conditions. It can increase building efficiency, improve environmental conditions, improve the quality of living, and create social opportunities. Afterlife is a design concept that works with existing structures and retrofits them for new, greener uses with prefabricated dwelling units and communal amenities. We propose to design housing units to inhabit the periphery of the slab, with the core area dedicated to adaptable communal amenities around a central atrium. The carbon-intensive parts of the building, the structural frame and slabs, will be retained. Sustainable materials will be used for the new insertions: timber frames or innovative insulation and cladding produced from agricultural waste. So how do we do this? First, we strip out the existing building back to its structure. We keep the core and create a central atrium to vertically and visually connect communities. We also update circulation cords to ensure they meet current regulations. We then analyze the building's orientation and prevailing wind conditions, and the off-site prefabricated dwelling modules are placed on the slab around its periphery accordingly. We exploit the surplus space to rotate dwelling units into the most favorable orientation. We strongly believe that three key features embody the basics of good quality housing. First of all, dual light exposure, to ensure a quality of natural daylight throughout various moments of the day and an outlook on a variety of exteriors with enhanced views. Second, private outdoor space, and the provision of a balcony to enable access to outdoor space. And third, natural cross-ventilation, to provide healthy airing of the internal spaces and assist cooling. The orientation and spacing of the units allows for cross-ventilation and good air quality throughout the slab, both for private indoor spaces as well as for the external communal facilities. The interstitial space is also used to integrate smart living features to enhance energy-efficient consumption and comfort control. Insulation is inserted in the gaps between the existing structure and the new inserted units, and more generally, utility rooms are located in the surplus space between dwelling units. One example is the insertion of heat recovery units between modules. We insert phase-changing systems in the interstitial space, allowing for panels with very high thermal capacity to absorb heat from incoming air, and as such, have cooled air entering dwellings on summer. PCM panels then release heat stored throughout the day into air circulation at night. Another smart living feature is the communal air source heat pump system, which is used for communal heating and water throughout the slab, as well as excessive PVs on the roof level. Throughout the scheme, we aim for passive house standards of the building fabric and the use of biomaterials for health and well-being. The exterior private space created through the rotation of each unit provides a generous, well-designed private outdoor space, as well as shading for the balconies on the south and west facades, thus avoiding overheating risk. This is an example of what a private outdoor area at a taller vantage point over the city could provide. The original cores of the building are then reconfigured into shared facilities. These become refuse and recycling rooms, or communal laundry spaces, storage rooms, basically facilities that benefit everyone and enable to dedicate more space to the dwelling units. Vegetation is generously inserted through an approach to biophilic design. We have communal landscape planting and gardens that provide food growing opportunities. Greenery on all floors is visible through the atrium and contributes to providing a quality of space. The core area around the central atrium is dedicated to adaptable communal amenities. These provide shared facilities and enhance social connections. They offer a variety of amenities, both indoor and outdoor, that residents will benefit from. The communal amenities are devised as flexible spaces, which can be accommodated at different locations on the various floors to offer a wide variety of uses for the community. These could range from wellness, such as fitness rooms, clinics, beauty salons, or one could imagine medical support unit, for example, for elderly living. There will also be living amenities such as cafe, communal lounge, or game rooms, or learning amenities for art activities and workshops. The residents will thus benefit from a sense of place and community in the building. We also provide an outdoor open space for playgrounds or sport activities, for example. All these social pods are modular and designed to adapt to a multitude of activities and sizes. The communal areas are a space for encounter and exchange for an active lifestyle. And beyond purely environmental aspects, This is also a way for us to use this interstitial space for better living conditions. Our thinking to create a more sustainable product also considers the technologies required to achieve this. The proposal is put together with an alternative construction methods and prefabrication. This allows for time and cost efficiency, an increase in quality as each component is created in a controlled environment, and the site is kept clean and organized, thus reducing waste. The modular units arrive as flat pack elements. They are assembled with materials that are energy efficient at a low cost thanks to rapid assembly. And it also reduces transportation emissions, further improving the sustainable outcome. In the future, we could also consider on-site 3D printing for creating atypical forms or possibly a cheaper and more efficient construction and better structural durability. To develop our material choices, we worked closely with BioHM. BioHM is a leading pioneer in the research of bio-based materials. Their ethos is set on creating a circular economy and minimizing environmental impact throughout the entire production process. They have developed a plant-based construction system from which the modular units could be built. This is a system where no permanent binders are required to strengthen material. And this means that off-site production is possible, reducing time and cost, and also that demolition as we know it is eliminated, as the components can be dismantled and reused differently somewhere else. The units are insulated with mycelium insulation, a vegetative filament root structure of mushrooms combined with byproducts and waste from other industries, which provide high standards of insulation from 100% natural and biodegradable material. And surfaces are made of ORB, food waste converted into a sustainable and aesthetically beautiful replacement of wood-based sheet materials. Again, this is 100% biodegradable, sustainable, and renewable. Working closely with our environmental consultants XCO2, we aspire to achieve a proposal which is net zero or even carbon positive over its lifetime. The most carbon-intensive part of the existing building, its structural frame and slabs, will be retained, and all new inserts proposed in natural and innovative biomaterials, which will drastically reduce the embodied carbon content and construction site impacts of the homes. Moreover, all construction elements will be modulated and designed to enable disassembly and repurposing at the end of the building lifetime. But Afterlife also considers the much longer-term potential of our built environment and embraces the reality of changing societal needs. The insertions can be fully dismantled, components recycled for new uses, and the original structure populated by new programs and functions over time. We can imagine what homes we want in 20 years' time, but as the recent events have shown us, projections change and are not always predictable. As such, the concept is designed to allow for change to be implemented in the future as our society evolves. Our aim with Afterlife is to show that if we can retain more existing structures through intelligent retrofit, we'll reduce carbon emissions and embodied energy costs, while improving the quality of our living conditions. We'll help conserve resources and set buildings up for a much longer life. I am convinced that there is a financial value of buildings that promote well-being, and that this will be an increasing demand from both investors and dwellers from now on. Afterlife is a cost-effective solution to respond to future housing needs and requirements. I hope this talk provided you with a new outlook on the retrofitting of existing structures, with novel proposals for increased environmental efficiency, and with an understanding of how we can embed flexibility of use for evolving societal needs with good design. I am eager to hear your impressions and feedback in the time we have left for the Q&A, or please feel free to contact us by email. Thank you.